Hello, everybody. So I need to talk a little bit about Faraday's law. And to do that, I want to set it up with a situation. So what we're looking at here is a magnetic field. This is a region in which there's a magnetic field, fields into the page. Here you have a loop of wire that is moving to the right. And as it does, it just moves through the field. What's interesting is if you actually tried this, when you tried to remove the wire, when it got over here to the edge and you tried to pull it out, what you would find is that you would have a current flow in the wire. As you were pulling this thing out of the field, you would get an induced current in the wire. Now, it turns out that you can use sort of the classical theory of magnetism to be able to explain this. And to do that, I've gone too far. To do that, you need to think about what's actually going on. You have this wire that has free charge in it, and the free charge is moving in a magnetic field. And when you have charge moving in a magnetic field, according to QV cross B, you're going to get a force on the charge. So the charge is moving along this line. Okay, the wire and the charge is moving this way. The magnetic field is into the board. Your thumb points up, which means positive charge is going to tend to be pushed this way in the wire. So it's going to get pushed upward, like so, along this line and along this line. And in doing so, you're going to get an accumulation of positive charge along this line and an accumulation of negative charge along this line. You're going to get a polarization. When you get over to this position, what's going to end up happening is you're still going to get this push of charge this way, but there isn't going to be any push over here because there's no magnetic field over here. And so effectively what's going to happen is the charge that gets pushed this way is going to get pushed, but then it's just going to keep going and you're going to get a current. So you can explain this using the classical theory of magnetism. Faraday didn't look at it that way, though. Faraday had a different way of sort of framing the situation. So what Faraday said was that you have a magnetic flux through the cross section, through the face of this coil. Okay, you have magnetic field lines that are passing through the face of the coil. That means you have a magnetic flux, and you can calculate the flux. Okay, B dotted into A. Okay, so it's a calculable value. What he observed was that when there was no changing flux, you got no current. Whereas when the flux was changing, here the magnetic flux, the number of magnetic field lines passing through is diminishing. So when you got a changing magnetic flux, then you got a current. Now, he could have tried to relate the changing magnetic flux to the current, but instead, what he related it to was the induced EMF, the induced electromotive force that was generated in the coil, which means we need to kind of do a little review. If you remember back with a power supply, a real live, real world power supply has two parts to it. There's internal resistance, and then there's the part that generates the electric field that motivates charge to move. And that part was quantified by what we called an electromotive force, or an EMF. Effectively, what Faraday was saying was that an EMF was generated whenever you had a changing magnetic flux through the cross section, through the face of a coil. And so he quantified it that way. He said the induced EMF equals minus sign. It turns out you need the minus sign for conservation of energy. We'll talk about that later. The proportionality between the rate of change of the flux with time turned out to be the number of wines in the coil. But basically, this relationship right here is Faraday's law. The induced EMF equals minus the number of wines times the rate at which the magnetic flux changes with time. If the change of flux happens quickly, you're going to get a big induced EMF, you're going to get a big current. If the change in flux with time happens slowly, you get a small induced EMF, you get a small current. You know that flux is B dotted into A, which in turn is B times A times the cosine of the angle. So sort of the working version of this relationship is going to be this right here. Okay. So quick example, you have a coil with 200 turns. It's a square coil, 18 centimeters on the side, which is like 0.18 meters. Total resistance is 2 ohms. Uniform magnetic field is turned on perpendicular to the plane of the coil. Okay. If the field changes linearly from 0 to 0.5 Webers per meter squared in the time of 0.80 seconds, find the magnitude of the induced EMF. Okay. So with everything constant, we can use the delta version. Don't worry about that. That's the only version you have available to you. And so there is your relationship. You've written this down. And here is the expanded version. And the only thing that's different here is instead of having B times A times the cosine, I've noticed that A is a constant. So I've pulled it out here. And the cosine of the angle is a constant, so I pulled it out here. And the only thing that's left inside the deltas is delta B. That's the only thing that is changing. And it's going from 0 up to 0.5. So there's the delta B. Here is what the area of the coil was, 0.18 meters on a side squared. Here's the number of turns, etc. There you have it. It's a typical, standard, easy Faraday's law problem. An extension of this would be to ask what the current was. And the thing that's important here is you need to understand that in these problems, Ohm's law still works. So in this case, the quote-unquote voltage is the EMF. So the EMF is going to equal IR. I is going to equal the EMF over R. You do the math. Another more sort of classic Faraday's law problem is the following. You've got rails, metal rails. They are connected to one another with a resistor in between. There is a beam of sorts that's made out, or a rail, well, it's a beam of sorts that is made out of metal. So you actually have like a circuit. There's metal here, wire, 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 metal. This is a circuit right here. There's no power supply in the circuit, but there's a circuit. And this thing is bathed in a magnetic field that's in the moving into the page. And this beam is made to move with velocity v in this direction. So this cross-sectional area is getting bigger and bigger and bigger, which is to say, if you think of this as a coil here, the flux through the coil is getting bigger and bigger and bigger. Okay, the number of field lines through the coil is getting bigger because the coil itself is getting bigger. So derive an expression for the induced EMF of the coil. The first thing you want to do with this is to write down the expression for the magnetic flux, because that's what's going to be changing. So to do that, you write out B dotted into A. Okay, and there B is B, and A is the area of this thing, which is going to be this length L times that length X. So there is phi. Induced EMF is going to be minus N times the change of that with time. Okay, well, B isn't changing, L isn't changing, X is changing. So you pull the constants out, you end up with the change of X over the change of T, which just happens to be the velocity. So this turns out to be the induced EMF. In what direction is the induced current in the circuit? You could use F equals IL cross B to figure out what the direction of the force would be on a charge carrier through here. Or you could use what's called Lenz's law, which is what we're going to talk about the next time we meet. And so I'm not actually going to do this problem because I'm going to wait until we talk about Lenz's law. Turns out it's going to turn out to be counterclockwise, but again, you don't need to really worry about that. What's the current in the wire? The current in the B field will feel a force. So if you have current flowing through here, and it's in a magnetic field, a current carrying wire in a magnetic field will feel a force. Remember, the force was IL crossed into B. Okay, well, there is our relationship. To do this, we know what L is. We know what B is. We need to know what I is. Okay, so once again, we're going to use Ohm's law to figure out I, and then we're going to put it into this relationship to figure out what the force is. And I believe that's as far as I took this. Yep, that's as far as I took this. So that is Faraday's law in living color, and it's something that you're gonna need to learn to deal with and be able to use. So that's it.